So now let's construct a Turing machine to construct unary strings to binary strings. So what does this mean? What is unary? Unary means base 1. So imagine if I'm given this string, let's say this string, right? This is my input string. I want, this is basically unary 5, right? Because there are 5 ones here. Now how do I convert this into binary, and what is the final binary value that I want? The binary value that I want is this. This is base 2. So this should be converted into this. This is what we want. So if you think about it, if you think of unary and binary, right? So if you have just one, binary is also 1. If you have 2 ones, this should become 1 0. If you have 3 ones, this should become 1 0 1. Right? If you have 4 ones, this should become 1 0 0. So this should become 1 1, I'm sorry. So not 1 0 1. 1 0 1 is 5, right? So 3 is this. This is 4. If you have 5 ones, it should become 1 0 1. So on and so forth, right? So this is basically base 2. This is base 2 and this is base 1. Now how do we do this? Okay, let's try to construct a Turing machine for this problem. So now in my binary, instead of using symbols 0 and 1, look at this. For my unary, I'll use the symbol 1. To avoid any confusion, instead of using 1 and 0 here, I'll use Z to represent 1. I'll use Y to represent 0 here. Okay, just for simplicity, to avoid the confusion between my unary alphabet and my binary alphabet, right? So this will be in ones, but the output will be in Z's and Y's, where Z equals to 1 and Y equals to 0. And how would my input look like? My input will look like this, right? So I have blank spaces. Let's assume my input consists of 5 ones, right? Again, then everything will be blanks, right? So this is my input string. Now let's start constructing the whole Turing machine for this, step by step. So I start in state Q0. So my read write head is here. I'll start reading it now. Okay. So what I'll try to do, again, the logic here is, okay, so the very important logic here is as follows, right? So while I'm reading my input here, where would I write my output? This is where I'm reading my input from. Where should we write our output? We can either write our output in this space or in this space. So what we will design a Turing machine which writes outputs on the left hand side of the inputs. This whole thing is my input. My read write header is always on the leftmost symbol of the input, and I'll try to write my output here, right? So let's go step by step. So how will I design this? Again, there are multiple Turing machines you can design. What I'm designing here is just one of the many Turing machines you can design that converts unary to binary. So this is my input and I want my output to be here. You can design a Turing machine where the output is on the right side, right? Here to simplify the problem, I'm using Z to represent 1, Y to represent 0. You could also create a Turing machine whose output is also in 1s and 0s instead of Z's and Y's. There are many ways you can construct it. I'm trying to pick the simplest possible way. Okay, so let's go here. So I start here. Look at this. I start here. Now, if I encounter, so the way I'll think about it is this. Okay. So the moment I encounter a 1 here, right? The moment I encounter a 1 here, see, I'm reading this, right? So what is the equivalent of unary 1? Unary 1 equals to binary 1. What is binary 1? When I'm using Z and Y here, this should be equal to Z. What will this be equal to? This will be equal to ZY. This will be equal to ZZ. This will be equal to ZYY. This will be equal to ZYZ. Right? So on and so forth. Because I'm using Z for 1 and Y for 0. The moment I read 1, I want to write the output here. Right? So let's go step by step. So for example, imagine if I'm reading 1. Right? I read a 1 here. The moment I read a 1, what do I want to do? Right? Because I've already read 1, I want to convert this blank space into Z, which is nothing but the corresponding base 2 value or binary value corresponding to whatever I've already read. Right? So what I'll do here is I'll start saying if I have 1 here, I'll replace this 1 with X because I want to mark that I've already read this. Right? I want to mark the fact that I've already read this. Right? And I want to move left. So now what happens here? This 1 which I've already read will become X. So let me change this to X. Right? And I'll move left. Right? So what will happen here is this. So this will become X. I want to mark the fact that I've already read this 1. Right? So I move here now. Right? Look at this. I want to mark the fact that this 1 has already been read. The corresponding binary value, I want to place it here. in place of this B, right? Very, very simple here. So now I've reached my state Q1. Now what should I do? I should now if I encounter a B here, what should I do? I should replace this B because I encountered a 1 here. I should replace this B with a Z. So let's write that logic here, right? If I encounter a B, I'll replace that with Z, right? And I'll move right now. I'll move right. Okay, simple. So I replaced this B with Z. Okay, look at this. I'm replacing this B with a Z. So what happened here? I've read the single one. I've also written its corresponding base 2 or binary value here. Cool. Till now everything is working well. Now what happens here? Look at this. Now, when I move right here, what happens? Look at this. It says move right because I've already written this value. So I move right, which means I'm here. Now when I encounter X, what should I do? I should just ignore it because that one has already been processed. The one that was initially here, that has already been processed and its corresponding binary value has already been written here. So I'll just ignore this X here, right? I'll simply ignore this X. So I'll continue to stay in the same state. I'll replace X with X and I'll move to the right, right? Everything is looking good enough. Okay, let's continue. So again, we can easily construct Turing machines with examples. Again, what am I doing here? I'm just taking some examples and I'm trying to construct Turing machine bottom up, right? I'm trying to go through each example and I'm trying to do this. That's all I'm trying to do. Now imagine if I have this 1. Now what happens on 1? I replace this 1 with X. Look at this and I move left. So what will happen here? This will be replaced. This 1 will be replaced with X. This 1 will be replaced with X and I move left, right? When I move left now, look at this. I have an X here. So this X has already been processed. So I'm in this state right now. Now if I encounter X, what should I do? Just ignore this X and keep moving left, right? Again, in some people write these transitions. So I'm writing this transition as follows. Replace this X with X and move left. This is how I'm writing it because this is easier to read. Replacing this with this and moving left. Some people also write this as XXL. This triplet. They also write it like this. So there are multiple, depending on which book or which articles you're following, this representation might change. Some people might write this as XXL. Some people also I've seen write this as X comma X by L. So there are multiple ways of writing this. So if you're reading a textbook where this notation or this notation for each of these transitions is mentioned, please don't worry about it. The concept is the same. The concept doesn't change, right? It's just a notational convenience. I prefer this notation because I can read this as X being replaced by X and moving left. I prefer this notation, right? So now what happened here? Look at this. I've replaced my X with X and I'm moving left, right? So where was I? So I replaced this X. I'm in this state. So this should move left now. Look at this. This will move left now. So I'm at Z, right? I'm at Z now, right? Now if I get a Z, what should I do? Look at this. Now I have 2 1s. Look at this. I've read 2 1s. I've read 2 1s. So when I read 2 1s, what should my output be? My output should be ZY. I have a Z here, right? Look at this. This is where my output is, right? This is where my output is. This is where my input is. This is where my output should be. Now I have Z. So I should replace this Z with Y, right? So replace Z with Y and keep moving left. And keep moving left, right? So now what will happen here? Because this Z has been replaced. Look at this. The Z has been replaced by Y. This Z has been replaced by Y. And I'm moving left because I need to still place my Z here. My output here, because I've read 2 inputs here. I've read 2 1s and I've marked these 2 1s as X. My output should be ZY. My Y is there. Now B. Look at this. This is cool. B should be replaced by Z and move right. Cool. So B will be replaced by Z. I already have the transition. B will be replaced by Z and I'm going to move right. Right. So now I'll arrive here. Now I will arrive here. Cool. This is good. Now what should I do here? I should not touch this. I should not edit this in any way. I should leave it as is. Till the time I reach 1, I should just not edit this. Because I've read 2 1s now and my output also corresponds to the binary equivalent of it, which is 10 or ZY in our context. So here what will I do here? Y, just leave it as is and keep moving right. Right. So just leave your Y as is, keep moving right. Now I get an X, keep moving right. X, keep moving right till the time I get 1 now. Look at this. Now when I get 1, look at this. Now when I get 1, what should I do? Again, are all transitions done? We don't know. Let's run through the whole example, right? So when I get 1 here, what should I do? 1 will be replaced by x. Cool, right? 1 will be replaced by x. So let me just replace this 1 with x, and I'm going to the left. When I go to the left, what happens? I keep replacing my x's with lefts. I keep replacing. Now I reach here. Now look at this. Now I reach here. Now what do I want? I want ZZ. I want ZZ. Now what do I see here? If you notice, what do I see here? I see a Y. I see a Y. This Y now, look at this. This X replaced with X. I've reached here now finally. And my state is still Q1. Now I have ZY. Because I've read 3 ones, it should be ZZ. So this Y should now be replaced with Z. Right? This Y should now be replaced with Z. And I can keep moving right. Then I don't have to worry. So if I just move this to Z, look at this. If I move this to Z, I'm done. I've already accounted for this and I keep moving right now. Right? Again, same. All these transitions will play a role. Right? Everything. Now let's go. Let's keep going forward. Now what will happen here? If you notice this X, if I keep getting X's, keep moving to the right. When I get a 1, replace that 1 with an X. Look at this. This X I'll replace with this 1. I'll replace with an X. And I'll go to the left. And now if I keep encountering X's, I'll keep moving back. If I encounter a Z now, look at this. Now I've read 4 ones. What should my output be? My output should be ZYY. So this Z will now get replaced because I'm in this state, right? Look at this. This X's got replaced with X's. I'm moving left here. Now I'm in this state. This Z will get replaced by Y. Right? This Z will get replaced by Y. Again, this Z also will get replaced by Y. Right? This Z also will get replaced by Y. This Z also gets replaced by Y. Then this B should get replaced by Z. Right? So this will become Z now. So let me erase that and write it down. So this will become Z now. So now I've read 4 ones and my output represents 1, 0, 0. I'm still again in state Q0. Right? So look at the whole flow. Now I'll again, if I keep getting Y's, I'll stay here. Right? If I keep getting X's, I'll stay here till the time I get 1. Finally, when I get a 1 here, what will I do? I'll change this 1 to X. I'll change the 1 to X and I'll keep moving left. Look at this. I keep moving left. Now, what is the corresponding value of this? The corresponding value of it is ZYZ. Now, what am I encountering here? I'm only encountering Y. Now, the moment I'm in this state right now, when I encounter a Y, what should I do? I'll replace the Y with Z. Look at this. I replace this Y with Z. And I keep moving right. Right? That's it. I keep moving right. And now finally what will happen? I'll encounter a B. Look at this. Finally I'm encountering a B. Right? There is nothing else left. So when I encounter a B, what should I do now? So now everything is processed. I'm left with B now. Right? I keep going forward. Now I'm left with a B. No more ones left. Right? So I'll create this one more transition here and say, if I encounter a B, keep it as B itself. Right? Keep it as B itself and move right. And I'll move to a final state here. Right? I move to a final state here. That's it. That's all. That's how you convert from unary to binary. Extremely simple. Again, this is very easy to do it with some examples. Again, the strategies that we learned when we started designing finite automata, wherein we take a bunch of examples. This whole state transitions, the only fundamental difference between your Turing machine and finite automata design is same example based approach you will employ here. But just remember how you are changing the symbols from one symbol to other symbol and whether you're moving left or right. So that's why we focused so much on finite automata design, because if you understand this, designing other forms of automata becomes much more easier, right? So this is one again, this is a very, very important task, right? Converting unary to binary. Again, this is like an input output device. This is not about language acceptance. Here, what do we have? Here, this task is not about language acceptance. This task is about a computer with input output. Right? This is a computer with input. Given an input, we are generating an output. This was the input that was given to me. I generated the output. Right? So very interesting approach here. Now let's look at one more thing. Right? One more problem here. Again, I'll also point you to many other resources. I'll show you some examples and explain them in detail. But I'll also give you more resources so that if you want to look at more architectural designs of Turing machines For other problems, you can go through them, right? So Turing machine for unary addition. So let's say how the input should be first. Let's discuss about the input. Again, here I have unary addition, which means I have two unary numbers and I want to add them. How can I input that? Look at this. I can input it like this. I have two zeros followed by a special symbol C, which you can think of it as a separator. So this represents 2 and I have blanks here. Look at this. I have blanks here. All of them are blanks, right? I have a C, then I have zeros here. So this represents unary 3. This represents unary 2. Here I'm using zeros instead of ones, right? You can use any symbol in unary. You can use A also. So there are 2 zeros here and there are 3 zeros here. And I want to add them. Now I have all blanks. Right? Look at this. This C is a special symbol that is used as a delimiter between your unary 2 and unary 3. You can use C, or some people also use plus symbol here because plus is also a symbol. Plus is also a symbol. I just need to have my plus as part of my tape alphabet. If I have my plus symbol as part of tape alphabet, I'm done. Right? So here you can place any symbol here, like a plus symbol or anything. You can place any symbol. We'll go with C. Right? C basically implying that C is a separator between my unary 2 and unary 3. What is the output that I want? Look at this. What is the output that I want? I want my output to be B, 5 zeros. Right? 5 zeros, because this is addition, right? 2 plus 3 is 5. This is what I want, right? And then I want B, so on and so forth, right? This is what I want to achieve. How do I design the how do I design the Turing machine for this? Not finite automata, sorry. So let's keep going with this. So let's keep going with it step by step. Now what we'll do here, instead of this type of arrangement, let me tell you the idea first. Okay, I'll tell you the idea, then we'll design the Turing machine itself. So what I'll do, I want 5 zeros as my output. But the way I'll go about it, there are multiple ways of solving this problem. What I'm showing you here is one approach. Just a while later, I'll also show you another approach of thinking about it. Just to show you that there are multiple ways of thinking about it. So what I'll do, I'll start reading my input from here, right? I'll start reading. So whenever I encounter a 0, what I'll do here, look at this. What I'll do here is, I'll just make it an X, right? When I make an X out of it, look at this. What is my input tape right now? My input tape is this. I'm just aligning everything, right? So when I read a 0, what I'll try to do here is, I'll keep my 0 as is. I'll change my 0 to X and I'll place a 0 at the end of 3. So I'm converting this 0 to X and I'm placing a 0 after this 0. So this stays here, this stays here, this stays here. Instead of this B, I'll place a 0. Similarly, I'll take this, I'll convert this into an X. Look at this, I'm converting this into an X, right? And then I'll add one more 0 here instead of a blank. Now, if no more zeros are left, what I'm left with here is equal to whatever I'm left with here, which is after this C, right? Is the unary addition equivalent, right? It's the unary addition equivalent, right? So this is one strategy of doing it. So let me write the Turing machine for this, right? We'll start with this example. This example should be good enough for us to construct the whole Turing machine. So I'm in state Q0. Let's go with it. So I encounter a 0. The first 0 that I encounter, I'll replace it with X. So when I encounter 0, I'll replace it with X and I'll keep moving right. So this 0 has been now replaced with X. Cool. Now I move here. Now if I encounter more zeros, I won't do anything. Look at this. If I encounter more zeros, I'll let it be as is. Because I only want to make one 0 as X and place a 0 here. Then I'll come back, make this 0 as X, place a 0 there, and so on and so forth. I want to do it step by step. So if I encounter more zeros here, I will not touch it. I'll just keep them as is till the time I encounter a C. Look at this. So now what happens here? So this is red. Look at this. This is done. This is done. Now I move to C here. Now when I encounter a C, what should I do? Keep the C as is. Don't touch the C, but move to the right. And I'm going to a different state here to know that yes, I've already moved over from C, right? Now here, if I encounter zeros, I don't want to do anything. Only when I encounter a B, I want to replace it with 0, right? So here, if I encounter zeros, I want to just keep them as is, right? So I keep moving to the right. Now when I encounter a B, look at this. Now when I encounter a B, I want to replace it with a 0. When I encounter a B, I want to replace this with a 0. So I'm replacing this with a 0 and I want to start moving left now. right? I want to start moving left now. Now when I'm moving left now, if I encounter zeros, look at this. If I encounter zeros, I'll just keep them as is and keep moving left, right? If I encounter a C, look at this. If I encounter a C, what will I do? I'll just keep moving left. Don't touch the C. Keep moving left. So this state basically means that I've seen zeros. I've seen the C also. Now I've come to the other side. I've come to the other side of C. That's what this state says. Now from this state, if I keep encountering zeros, look at this. If I keep, suppose that there could be more zeros also here, right? There could be more zeros. I'll leave the zeros as is. I'll leave the zeros. I'll keep moving left. But when I encounter an X, this means that, okay, no more zeros to the left of it, right? So when I encounter an X, what should I do? This whole process that I've done should repeat. So what I'll do here is this. So when I encounter an X now, I'll keep the X as is, but I'll move right. So now where do I move? Now I move here. Now this whole, what is this whole cycle doing? This whole cycle is taking a 0 here, replacing it with X, move forward, replace this 0, replace this B with a 0 and come back here. Right? That's what this whole cycle is doing. So if I repeat the whole cycle, what will happen? This will become X. It will go forward, C, nothing. Keep going forward till the time it encounters B. When it encounters B, it will replace this B with 0 and it will start its trajectory back. Once it moves back, what happens? Finally, I'll reach here, right? This whole loop finally. So this whole part, X, when I encounter X, I'll keep the X as is and I'll move here. Once all of my input is over, what happens? Look at this. When all of my input is over, right? When all of my input is over, I'll encounter C. No more zeros left here, right? So when I encounter C, what should I do? I should change my C to B and move right and go to a final state, right? So this becomes my final state. So what do I do now? This C, I'll convert it into B. So this C, I'll convert it into B, right? Now what do I have? Look at this. What do I have? I have my 5 zeros that I want here. Again, this is one of the Turing machines for Unary addition. We can also design other Turing machines also. And look at how we designed this Turing machine. Again, we first design a logic. This is one of the possible logics for Unary addition. I'll show you one more logic so that you understand that there could be multiple logics or multiple ideas on how to construct Turing machine. Once we get the logic, once we think of the basic logic on where the input should be, where the output should be, how should we work? Again, remember that this is an input and output machine. This is an input and output Turing machine because we are giving it 2 inputs and we're getting an output. And then designing all the transitions and all is straightforward if you are just using examples to construct it, right? So let me show you one more way of doing it. So Turing machine for Unary addition with a completely different logic. Okay. So here let's assume I have 1, 1. Look at this. Imagine I have my tape consists of these symbols. Ones. Again, for Unary, all these are blanks. All these are blanks, right? Here, if you notice, my Unary 2 is represented using ones. Again, I can represent using zeros or ones, doesn't matter. Okay, my alphabet changes, that's it. This is 3 and I have a special symbol called plus here. Now let's see one more strategy of doing it. One more idea of solving this problem is this. What I'll do here is I'll keep the B's as is. Okay, I'll keep the tape symbols as is. I'll keep this 1 also as is. I'll keep this 1 also as is. I'll change this plus to 1. Look at this. I'm changing this plus to 1 and I'll remove this 1. This 1 stays the same. This 1 I'll make it as blank and the blanks stay the same. So what am I doing here? I'm just changing the plus to 1. Okay, this is another strategy, right? Again, here you see this. You have 2, you have 3 and you have 5 here. This is another strategy that I can employ. What we saw here is one strategy where we are taking each of these symbols, converting them into X, going to the very right and placing the symbol there, right? Placing the zeros there. This is one strategy. The other strategy, much simpler strategy here is change this whenever you encounter a plus symbol, change it to 1, go to the very end, change the last one to B. That's it. Now, how do we construct the Turing machine for this? Let's go. Q0. This is where I start. Look at this. I always start here. If I encounter ones, just keep moving right. Don't touch it. Okay. Keep the ones as is. Keep moving right. Only when I encounter plus. Look at this. Only when I encounter plus. Change the plus to 1. And keep moving right. So this 1 has been changed to, this plus has been changed to 1. This is as is. This is as is. This has been changed. Cool. Now I keep moving right. If I keep getting ones now, look at this. If I keep getting ones now, So let's call this state as Q1. If I keep getting my 1s, I'll keep moving right till the time I keep getting 1s. Finally, I'll get a B. Look at this. When I get a B, I have to go one step back and convert this. That's what I have to do, right? So if I get a B, look at this. Now I'll keep moving right. I'll encounter a B somewhere. If I get a B, keep the B as is, but move left, which means now I have moved here. Look at this. Now I have moved here. This 1 should now be changed to a blank, right? So what will I do here? Now I'll change this 1 to a blank, right? I've changed this 1 to a blank, right? Now what will I do here? Now I've changed this 1 to a blank. I'll go back to check whether this is also 1 or not, right? So I'll go left here. Once I go left here, then again, I want to check. Look at this. This has been changed to blank, right? Now I go back here. This is 1, right? So this has been changed to blank. So where am I? I'm here. Now I want to see if this is the end or not. Just double checking it here, right? So whether this is 1 or not. So what will I do here? I'll say if my current input is 1, keep it as is. If my current input is 1, just keep it as is, keep moving right. Now here, what will I say here? I'll say if my current input is blank, keep the blank as is and keep the blank as is, move right and just accept it. That's it. Look at all the steps that I'm doing here. Okay, step by step again. Okay, so if I encounter 1s, I'm not touching them. I'm just keeping them as is. That's what this is doing. If I encounter 1, I'm changing it to a 1. If I encounter plus, I'm changing it to a 1. If I encounter 1s, I'm not touching it till the time I encounter a blank. When I encounter a blank, I keep the blank as is. I go to a previous state. Look at this. I go to the previous state because I'm moving left here, right? I go to the previous symbol. This previous symbol, if it is 1, change it to blank and again move left. Just ensure that this is the last one, right? Now, if this is 1, I go to right, and if the next one is B, that means this is the last one. Just ensure that and we reach the final state. Look at this. This Turing machine is different from this Turing machine, right? Look at this. Here you have a cycle. Here you don't have a cycle here, right? So even if you change the symbols, instead of plus if you write C, instead of 1s if you write zeros, the whole architecture of the Turing machine itself is different. By architecture, I mean the whole Turing machine itself is different. By architecture, I don't mean that we still continue to have the input tapes, we still continue to have the finite control, all of it stays the same. But if you look at the transitions and the states that you have here and the transitions that you have, this is different from this, which means for the same problem where you want to perform unary addition, you can come up with multiple Turing machines. And this is very similar to writing different C programs. Imagine if somebody gives you a task. You might write one C program, your friend might write a completely different C program, but both of them might be solving the same task. Just like the way, because a Turing machine is exactly like a modern computer on which you're writing programs, right? Two people can write completely different programs, but both programs could be correct, right? Just wanted to give that example through the unary addition here. Again, I'll also share some links of other Turing machine examples. Those of you who have time, who want to go through other architectures of other problems, please feel free to go through those examples. Again, with this, if you want to ever design a Turing machine, always start with examples, define what your input is, where your output will be, come up with a simple strategy to do it. Given that all you can do here is you can change the tape symbol, you can change the state, or you can go from one state to other state, and you can go right or left. Those are the tricks that you have up your sleeve, and you can try whatever you want after that.